Hello fellow problem solvers. So today we're going to be doing a problem from the 2022 Junior Balkan Math Olympiad, problem number 2. I was a coordinator on this Junior Balkan Math Olympiad on problem number 4, not on problem number 2, but it's a nice geometry problem that I suggest you can try out for a minimum of 20 to 30 minutes. And it is especially good if you're okay with like some basics in geometry you've done, like you can figure stuff out if it's just angle chasing or if there's one similarity or two. Maybe you've added a point on a couple of those like introductory problems. And then this problem is like a good next step. And ideally you would try it out for about an hour and a half to 2.5 hours. Like especially if you're there, not more than 4 hours, you wouldn't really have that much time at the JBMO. Like you have 4.5 hours for the exam. But this is problem number 2. I'm assuming you've tried everything else out in the first half an hour. So now, with that in mind, if you'd like to go along with us, draw the diagram, put your first ideas out on paper for the next 5 minutes. So let us begin. Let's read through the problem and see what is happening in geometry. You want to see what is new, what is different, what is old. So we have a triangle, acute. Okay, this is very regular. And then, whoa, AH is HD. This is new. What does it mean that the orthocenter is the midpoint, is at the same time the midpoint of the altitude from A? Interesting, right? Like this is new. And then we have, okay, a tangent to this circumcircle. S and T are the intersections. Okay, and then we have M and N. Okay, M and N are pretty basic standard. They always come up. But here, the question is, given this, how does the whole triangle change, right? That is the big question here. So let us, clear up the board and draw the diagram. So now that we've cleared up the board, let us, figure out, okay, what do we need? We need H to be the midpoint. So how are we going to draw the diagram? Well, for me, I'm first thinking, okay, I'm going to have A, I'm going to have my D, and then the midpoint here is H. And the reason I'm not drawing B and C first is because I don't know all the types of triangles for which this is true. But if I first draw the orthocenter and the foot of the perpendicular, then I can sort of figure out this is the line BC, and I'm going to pick where the points B and C are. And you see, okay, I can first pick B without any loss of generality. Let B be here. And now I can't just pick any C. I need to construct a C such that this is the orthocenter. How do I do this? Well, a couple of things. You can say, I'm going to just say one thing that's like a general good idea how to think about a problem differently. If H is the orthocenter of ABC, then C is the orthocenter of AHB. And A is the orthocenter of BHC, and B is the orthocenter of AHC. Right? You can, like, this is purely by definition. I mean, yeah, purely by definition. So with that, I know that C is the orthocenter of these 3 points. And then I know how to construct that. And the other way is just to say, okay, wait a second, BH, here I go here, and I take a perpendicular, I intersect it, and booyah, here's C. This is D, I don't have points E and F, so let's make this E. And let's make this point over here, kaboom, and F. Okay. So next we're having, okay, the first thing to do in introductory, like these levels, these types of geometries, and in general, I would say, is you try to angle chase, see what you have via the elements of the triangle. So for me, I'd be like, okay, alpha, beta, gamma. So if this is gamma, this is 90 minus gamma. Okay, so this is beta, 90, right? So this is 90 minus beta. And then this is 90 minus alpha, similar reasoning, 90 minus gamma, 90 minus beta, and then 90 minus alpha. And then I also have these angles, right? And these could be important. Like there is this circumcircle on BHC, so perhaps there's an importance to that. So let's call this, so this is gamma, this is beta. And now we have this good old-fashioned tangent. Okay, look at that. Now, how do I know it's a tangent? Well, the way we define tangents usually, and a good way to think about them is this angle over here is the same as this angle over here. That's a tangent. What is this? This is 90 minus gamma. So Okay, I'm gonna need to make this a bit bigger instead of that. I'm gonna make it like kaboom. And now here we have a 90 minus gamma, or here we have a 90 minus beta. And now with that, we have the points S and T. And now M and N are sort of like an added, if you think about it, M and N are sort of an afterthought. Oh, and then you have these midpoints. Maybe it's useful in some way, maybe not. Who knows? But let's see, what do we have for this? Pause for 5 minutes and figure out what do you have for these points S and T now. And the answer is, well, okay, this is 90 minus, what's it called, beta. This is 90 minus alpha. So this is 180 minus alpha minus beta, which is gamma. And now, analogously, this one is beta. So we have this angle, and we have that this is then 90 minus beta. In other words, yeah, these react collinear. This is 90 minus beta. This is 90 minus gamma. Who knows? Maybe this is useful. Maybe it's not. I don't know. Okay, this is beta and this is gamma. And we know that. So, okay, EF is also parallel to ST. Maybe it's useful. And here's the thing. When you're on these competitions, like I've graded now these exams and this level of competition. So write everything down that you notice. Write every single thing down. You don't just write, oh, these angles are alpha, beta, gamma. Here, no, you write, let BAC be alpha, let ACB be gamma, and ABC be beta. And then from there you say, okay, and now I have the angle ATS, AST is this, Y, you say Y, you just write these things down. You can have a last page of this thing you're going to, the thing you're going to give, like hand in. You can put there all the facts you figured out. And then, you can say, oh, I had this fact, or your team leader or deputy leader of your team could go ahead and say, oh, yeah, they had this fact. So now we have this thing for S and T. And we now need to connect somehow this to the midpoint, which is over here roughly, and which is right, and then I'm going to say roughly here. Now, okay, I'm going to move them around a bit just to make it so that they're parallel on my diagram as well. And there we have, these are the points M and N. And now the big question, the problem question is, how do I connect N and T? What is this, right? What am I even supposed to do? How do I connect it? And that's one of the questions. The other one is how do I also connect H as a midpoint? What is happening here? Okay. So there are a couple of ways we can go about, trying to connect this. And it really depends on your flavor, your style of geometry that you're after. My style was, okay, I have H as the midpoint. Let me try to, use this fact in some way, shape, or form. Well, I have that AH times AD is equal to AE times AC. Okay, but I can write, instead of AH times AD, I can write AH squared, right? I can say AH times AH times 2, because AH is, twice this. So I can go ahead and say AH squared times 2 is AE times AC. And now I could take the midpoint of AE and try to connect it with the other things in the problem. Like I can try to connect the midpoint of AE with this. Difficult with M and N, that's difficult. Or I can take the midpoint of AC. And I can say call this point K. And then I'd have, well then this is equal to AE times AK times 2. Because AK times 2 is C. Right? And what does this give me? Well, this gives me that AH squared is, AE times AK. AE times AK. And now what does this give me? Well, and this is, mind you, just the way I look at these problems. And I'm also putting this midpoint because I can connect it to N in some way, shape, or form. Perhaps. Now this gives me what? AH squared is AE times AK. So that means that this angle over here, right, if AH is then the tangent here, That means this angle over here is equal to this one, which is equal to gamma. And then what does this tell us? Well, it tells us that this here is gamma, this here is gamma, so HK is parallel to BC. I didn't have that before, but now I do. Isn't that cool? Yes, it is. So, what's it called? Now that I have this is gamma, and also you think about it, it makes sense. Like, wait, this is the midpoint here, this is the midpoint here, so of course this is going to be gamma. How did I not see that previously? Oh my God! How did I miss that? And it's okay. Okay, so I have K now as the midpoint. And mind you, this is just like one idea that I'd like to go with. Maybe look at, okay, are there anything, is there CH times this? Can I have anything with that? Also, this is beta. And like, wait a second. If this is beta, then BSTC are concyclic. So I have AT times AC is equal to AS times AB. Maybe there's something to do there as well, right? If I now put in the other midpoint here, call this K, call this L, the other midpoint, I also have AL times AS is AT times AK. I have LHK are collinear, SHT are collinear. This is a cyclic quad. Maybe there's something to be found there. Who knows? I don't see it just yet. But like there's analogies that we can then come up with. Also, we could say AD squared is equal to, what's it called? 2 times A. Now it's AD squared over 2. So I need to actually extend something by 2. Perhaps that's another idea. And then, okay. Let me see what else I have. Maybe I've been adding points way too soon. Let me see what I have here. I have this is 90 minus beta. Okay, 90 minus beta, 90 minus alpha. Okay, I have these are similar. I also have these two midpoints. So this is the midline. This is parallel to this. So this is 90 minus gamma. Oh, and this angle over here is 90 now. Who knew? What an interesting thing. Wait a second now. This is 90 minus gamma, and so is this. Pause for the next 5-10 minutes, try to push the problem further. And I just realized that as soon as I said this, like, wait, I could have told you to pause. So here now it seems like, okay, wait a second. So these four seem to be then concyclic. So N, K, T, H lie on the same circle. And now, this means because this is 90, that means this angle over here is 90. So NTS is 90. Well, similarly, I should have this over here be 90 in the same way, and this be like there's analogy when you have similarity. So then this angle over here is also 90. MST is 90, and we are done. Like this is just going at the problem forwards because now the sum of these two angles is, what's it called? 90 plus 90, 180, so they're parallel. As simple as that. Problem solved. Now this was one way of thinking about it. Another reason why you might want to put this midpoint specifically, K, outside of this PowerPoint bonanza is because H is the midpoint and you can connect the K, you can connect to both H and N if you put it as a midpoint. Right, the problem with midpoints in geometry, and especially if you're solving everything synthetically, is how do you get angles from midpoints? Like that is the, oh my God, the difficult part. And here's how, right? You're trying to find, like here we had like two midpoints and we try to connect them somehow. Like, okay, these two are connected, this is parallel, but you're trying to connect them somehow. And the way to do that is usually, generally, not always, but a good heuristic to have is try to find a new midpoint that sort of connects the two in some way, shape, or form. And with that, we finish the problem. Now there's a different way of approaching this, a different way of thinking, which I'll show now. So this second approach asks this question, wait a second, what angles did I have here? I had here 90 minus alpha, and I had this angle was 90 minus beta, because this angle over here was actually, no, 90 minus gamma. 90 minus gamma, because this one over here was 90 minus gamma, this is beta. Okay, so question, I have the midpoint here. Is there any other triangle that I have with angles 90 minus alpha, 90 minus gamma? And then this midpoint. Because then I can maybe find some angles or some relationships with angles if I find my corresponding similarity. And this is a different, literally the second most common way to come up with ways to connect midpoints in triangles in a synthetic way. Okay, let me find another triangle which also has a corresponding midpoint and which may be able to give me some other angle that I didn't have, right? That is the next idea. So which triangle has 90 minus alpha and 90 minus gamma? Okay, I need to look at 90 minus gamma. Well, over here is a 90 minus beta. I don't have it. Darn. And now I have 90 minus gamma. And now, wait a second, if I connect D and E, I know this is 90 minus alpha because what's it called? This is 90, this is 90. These 4 points are concyclic. And you also just know your angles from these general configurations. So this is 90 minus alpha, 90 minus gamma. Okay, so this could be like our candidate, AED. Could be the similar thing that we're dealing with here with HTC. Now what is, so here we have an N, what corresponds? Okay, it's on HC, so that means it's on AD, it's H. It's H. Yeah, it's H that we're looking at. So this means what? It means that, mind you, because the triangles AED is similar to a triangle. Okay, so A is 90 minus gamma, H has 90 minus gamma, E has this angle that's obtuse, so does T, and C. And now if I take the midpoint, you can look at it as, now from this we have HT over HC is equal to EA over ED. Actually, no, it's AE over AD. And then if we take the midpoints, we still have the corresponding ratio that we need. And we have the same angle, so side angle side, yay. Yeah, side angle side. So actually let me write that down. What do we have? We have, I'm gonna take this midpoint, so I'm gonna have HC over AD, or over DA, is equal to HT over AE. Now HC is 2 times HN, 2HN, and DA is 2AH. You cancel these out, you have HN over HA is HT over AE. Combine this with the fact that this angle is equal to this angle, that the angle, what are we gonna have? Gonna have NHT is equal to the angle EHA, no, EAH. And these two combined give us that the triangles NHT is similar to, so NHT, then we have HAE. HAE, A corresponds to, just double check, A corresponds to this, T corresponds to E, N and H correspond to one another. And what does the similarity go? Well, here we have the angles, here we have this is 90. So that means that this angle over here is 90 as well. And this then finishes up our problem the similar way it did before. This is then also equal to 90, like equal to this angle, which is 90 minus beta. And so we finished the problem. Another, like a third option that I couldn't really make work, but that exists is, like there's potentially a way to go ahead and solve it. Mind you, Tn is parallel to AO now because this is 90 minus beta, that is AO. And the reason we might want to put in AO, assuming we don't know any of this, is there's a lemma that we know. And this is the third way, theory heavy, not a huge, humongous, and like it's useful in geometry to have a lot of theory background, but I don't know, it's like less fun that way sometimes. So what do we have? We have, if we take, why do we take an O? Well, we know by a lemma that, what's it called? If I take O and the midpoint of BC, call this B, and also this midpoint ain't so bad because it connects N somehow, and M. Now, how does it connect to T and S? We don't know. But this midpoint over here, if we take it, we know that this is equal to half of this. I've already made a video on this lemma. The way you prove it is by introducing another midpoint here, and then proving that these two triangles are similar. With similarity, that's like you prove by angles that they're similar, but you have that their similarity ratio is 2. And with that, we know that OP is half of AH, which is HD. So now OP is half of HD, which means what? Well, O lies on MN. Why? Well, it lies on MN because M's distance to BC and N's distance to BC, like MN is parallel to BC. So the distance is constant, and O is on this side of BC and has that same distance, so it's on this line. And now we have, okay, we have these are collinear. And we have, when we take this 90 minus beta, we have this is perpendicular to this. And now I want to prove that like sort of AO is parallel to TN is parallel to SM. And my question like this is maybe a challenge for you. Can you go ahead and try to prove that? Maybe I'm not really seeing something, but yeah, just don't see a way out of, like a way to prove this. Like I know that this over this is equal to this over this because these are similar. ATS and ABC are similar, and then I can, have maybe this over this is this over this. And I also have that this over this is equal to ON over OM. But from there, it looks like something that's well known in geometry, like maybe, but I don't think that like, does that give me enough information? That's my question mark that I'm having over here. Like if I don't know that any two are parallel with each other, does this really give me any information? Or like what else do I need? Can I get Tn somehow over, call this point say P? No, I already have P. Call this point Q. Can I have OQ somehow over Tn? Like how do I get to Tn if I don't know these angles? And yeah, that is the question that I'm having. Another approach that I did not even, that I didn't consider myself, but I was thinking of, and maybe you have an idea that you could finish up with and consider it, is, okay, what if I intersect this circle with, say, AC one more time at point, say, X? Does this give me anything nice, knowing that HT squared is TX times TC, and the fact that I actually, have this angle, I have H, I have this angle over here is 180 minus this angle, which is 90 minus gamma. So this angle over here is 90 minus gamma. Do I have anything with that? Oh, well, maybe this AX I can then use because I have AE times AC. Now I can maybe get that AD. Actually, let me try to figure this out. So I have X, I have this is 90 minus gamma, which is equal to this. So X is sort of the reflection of A with respect to E. So I have this AH, H times AD. This is equal to AD squared over 2, right? Because AH is AD over 2. And this AE times AC, well, this is AX over 2 times AC. So I have AD squared is AX times, what's it called? Interesting, AX times AC. So that means that this angle over here is 90. Is there anything interesting now, given that this is that X is the foot of perpendicular, that DX is now parallel to BE? I don't know. I'll leave this one to you. If you figure out a way to actually not, use this and connect this thing with what's it called, with S&T and our problem condition that we need to prove, please do let me know in the comments below. Now, this finishes up like a couple of explorations about this problem. And I just want to say one thing about general, writing down these proofs. If here's a little bit of a strategy. If you're short on time and you just want to put in a couple of ideas on your paper, and you have midpoints, add the midpoints, write something about them, just like write, let's consider this midpoint, like at the end. Because then your team leader can go ahead and say, oh, they've actually put in this midpoint, right? And everything you put in, write it down and just give it. And then the coordinators like myself, we will have, some trouble going through your paper, but it might give you more points at the end. That's just the strategy here. And this finishes up our problem. And as always, thanks for problem solving.